Hello everyone, my name is Paranjay Sharma. I am a student at IIPS DAVV. This video is regarding about my assignment for the subject Introduction to Data Science. I am currently in my 5th sem of MCA. So we were in this playlist of discussing solutions of end semester examination. Um, so we were on the question number 8. The part is ask us to asks us to compare decision trees, random forest and boosting, highlighting their strengths and weakness for each. So starting with decision trees, its strengths are it's easy to understand and interpret. It handles both numerical and categorical data. It's fast to train. It's In random forest, the strengths are it has high accuracy, it reduces overfitting, it works well with large data sets. In boosting, the strengths are it's very highly it has a very high predictive accuracy. It focuses on difficult data points, it reduces bias. And in weakness of decision trees, we have it's prone to overfitting, it's sensitive to small data changes, it has lower accuracy on complex data. In random forest, the weaknesses are less interpretable than a single tree, like it has multiple trees as we know. It requires more computation, it's larger model size, so it requires more memory. In boosting, it's sensitive to noise and outliers, it has a slower training time, and it's harder to tune and understand. And as for a summary, we can say that it's simple but weak alone. If we are talking about decision trees, it's simple but a single tree is not enough. In random forest, it's strong and stable, and in boosting, it's most accurate but it's highly complex. For example, if we want to see a simulation over here for decision trees with lower depth of trees and dataset noise is somewhat higher than usual. So if we train and visualize, we can see that it also captures some part of uh, the prediction which are of the other category. So decision tree is not singly reliable. If we talk about random forest with the same thing, it too does that. But if we talk about boosting algorithm, it has the least amount of uh, failed positives, the false positive. So that is how the strength and weakness is compared, and how we can visualize between these three models, which is decision tree, random forest, and boosting. Moving on to the next part, which is moving on to the next part, which is about showing how basic logic gates can be built using single layer neural networks. So this was the table which was given to us in the question for completing. So we have 4 gates: and, or, not, and XOR. So number of neurons required for these 3 gates are single layer, but in XOR we have to have minimum of 2 layers. The activation function for these 3 gates is step heap side, or we can say y equal to mx plus c. But in XOR we have to have step as well as sigmoid, which we learned previously, that is 1 1 divided by 1 plus e to the power the input. Then back propagation, do we need back propagation in these 3 gates? No, but back propagation is required in XOR. It is due to because it is linearly inseparable. XOR is basically linearly inseparable, which makes a single neuron, impossible to predict its output. So we have to have used two-layer neural net minimum. So that's how the table is done. For multi-layer perceptron, we have to use back propagation over here in XOR. This is a basic simulation. Thank you for watching the video. I hope you like the video. The playlist ends for the end semester examination now. Thank you.